Okay. Let me start with a few announcements. Homework number 1 is due today. If you've done it, hand it in at the beginning of the class. I don't like people doing the homework in the middle of the class. Homework 2 is chapter 3 from Oppenheim and Schaefer. It's on Z-transforms, which is what we're going to start today. We'll have a makeup lecture this coming Monday from 9:30 to 11. Make sure that you can attend it, or else watch the live webcast from wherever you are, or else just watch the video later on in a non-real-time fashion. I did talk to Mike Gaspar about 120. One of you, I forgot who volunteered to give me his notes. Is that person here? From the year or the semester he took Gaspar's course. And then there was another person who promised to give me her notes from Joe Kahn's. Is that person here? What? They disappeared? They looked at the notes, they said, wow, do I want to take another course in this area? So one of them was, what were their names? You guys, pardon? One of them was what? You won't get punished if you don't get into it. It's just a volunteer thing. Okay, so shall we do another round of volunteers? This time I'll write down the name. Anybody want to bring their notes from Gaspar's class? This is purely for me to know how much I should emphasize each topic. There's no grading effect if that's what you're worried about. Did everybody from Gaspar's class drop the course already? So nobody wants to volunteer? No? Okay. Anybody from Kant who wants to volunteer? Okay, what's your name? Miriam who? Mm-hmm. Can you bring it on Monday? Thanks. Anybody from Gaspar's? Nobody. How many people took it from Gaspar's course? You raise your hand. Yeah, it was you, wasn't it?
No, not me.
Did you? You're not a guy who volunteered, no? Okay, who took it from Gaspar's class? Raise your hand one more time. Okay, there's got to be the 10 of you. One of you should volunteer to bring it. Thank you. What's your name? How do you spell it? Okay, thank you.
Yes.
Oh, you did bring it. Very good. Thank you very much. And this is the homework?
Yes.
Okay, so this is from Gaspar's or Kahn's? Okay, so you don't have to, Miriam, you don't have to bring it. And the other person, you can still bring the, yes, okay, thank you. So what I'm going to do is I'm going to give this to the course admin, who is Rosita Alvarez. She's going to make a copy for me, and it'll either be back on Monday or on Wednesday. Okay, thank you. Okay, so let me get going with the lecture today. So last time we talked a little bit about sampling and upsampling, and sampling and downsampling. That's a sort of a reminder from 20 and 120. I'm going to do a fairly quick review of Z-transforms. I did talk to Gaspar. He thought that he covered the Z-transform quite in depth. So, and I assume that people from Joe Kahn's class also cover Z-transform quite well. So I will go fairly fast over it, probably in today's lecture and maybe half of Monday's lecture. So let me start by motivating why we care about Z transforms. What is Z transform and why do we need another transform? Why isn't the Fourier transform would not do the job? Anybody?
For some signal does not converge, the Fourier transform does not exist.
Right. So the answer is that there are some signals for which Fourier transform doesn't exist, and it doesn't exist because because the sum doesn't converge, and so Z transform is sort of yet another tool that people can use in order to manipulate those set of signals or design systems with Z transforms or other things. So, the main motivation is that Fourier transform just doesn't exist for some signals. And can any of you come up with an example of a signal for which Fourier transform doesn't exist?
Alpha to the n times u of n, where alpha is greater than 1.
Right, so if I have x of n, for example, 2 to the n times u of n, or if I have x of n equals a to the n times u of n, where magnitude of a is larger than 1, this is a geometric series or geometric sequence, and the terms get progressively bigger, and the Fourier transform for these things just does not exist. Okay. And from what you know from 120, what's the formal definition of Z transforms? If I have a sequence x of n, its Z transform is given by Z transform of x of n is given by x of z, and by definition, it's the summation over n x of n z to the minus n. Okay. So, and this n goes from minus infinity to plus infinity. By just staring at this summation, you can see that the Z transform is closely related to Fourier transform. And in what way? Well, Fourier transform x of omega, when I say Fourier transform of a sequence, I automatically mean discrete time Fourier transform. The DTFT of x of n is given by a similar summation, a summation over n x of n e to the minus j omega n. So if I stare at these two summations, right away it becomes clear that there is a relationship between x of omega and x of z. And what's that relationship? Well, it's pretty straightforward. X of z evaluated, if I replace here of z with e to the minus j omega, then I get just x of omega. Okay? So in words, what that means is that Z transform evaluated at unit circle, this e to the minus j omega is unit circle, just corresponds to Fourier, discrete time Fourier transform. Let's talk about this animal x of z just a little bit. I never told you what z is. What is z here? Omega, if you remember, was a real variable. Okay. And z here is what? It's a complex variable. And probably most of you have not taken a course in complex variable theory. But we'll talk about some of the properties of x of z and some of the complex variable theory stuff in this course. So when I say it's x of z is a complex variable, what do I really mean? Well, to plot, well, there's two things I'm talking about. There's the value of the function itself, and then there's the variable, what it's a function of. Okay, x of omega, it was a complex function in that this function had a real part and an imaginary part, but it was a function of a real variable. Okay, x of z, not only is it a complex function, but it's also a function of a complex variable. So what that means is that for x of omega, let's say I was going to plot magnitude of x of omega or something like that, I would only have this real variable omega, and I could draw something like that saying, if it was a band limited signal or something. But for x of z, when I plot it, this guy z is a complex variable, so I can talk about real part of z, and I can talk about the imaginary part of z. Okay? And so because z is a complex variable, then it's a two-dimensional plot, and if you can think about it, magnitude of x of z, for example, is a 2D function sticking out of the board, okay, as like a mountain or a cake or whatever you want to think about it. And this e to the j omega guy is just a circle. When omega equals 0, you get 1, and then omega changes all the way to pi over 2. You get I, then or j, if you will, and then this corresponds to, so this is omega equals pi over 2, this is omega equals pi, this is omega equals 3 pi over 2, this is back again to 2 pi. Okay? So z, the bottom line is that z is a complex variable, and it has a real part plus j times an imaginary part. Okay? On the other hand, x of omega was a function of a real variable, and it sort of repeated itself like this. And so what do I mean x of z is x of omega evaluated on the unit circle? That means that, think of x of z as a mountain sticking out of this plane, this paper plane here. That means, like, if I had a knife, let's say this is my knife, and if I were to cut it and go across the circle, and let's say then where the height of where the mountain would cut the knife corresponds to the height of this thing. So when I say at omega equals 0, x of omega takes on the value, I don't know, 5 or something like that. That means that if I were to evaluate x of z at this location, I would get the value 5, sticking up this much. And then as I traverse this way, all the way get to pi over 2, for example, it goes all the way to 0, which is the bottom. And then it remains 0, 0, 0, and then it comes up again and gradually comes up from here to here. So that's what we mean. If you can think of it, if it was a birthday chocolate cake, as you traverse the knife around this circle, okay, the height of what value the cake is an uneven surface. Let's say it wasn't a flat cake, it was bumps and everything. The bumps in the cake tell you the value of x of omega as you traverse along this circle. Is that clear what we mean by this is x of z evaluated on the unit circle, right? It's a two-dimensional sort of surface sticking out. And so another thing, so complex variables like z, not only you can write them as having a real part plus an imaginary part, you can also write z in terms of polar coordinates. It's r times e to the j omega, where r is sort of the radius of, or you can write it as r naught times e to the j omega naught. So if I have a point, let's say here, the distance from here to here is r naught, and then the angle here is omega naught. Okay, so that gives me the value z naught. Okay, so I can write a complex number like z naught either in terms of its real part, which would be this distance, plus its imaginary part, which is this distance, or I can write it in polar form, which is the distance from the origin times e to the j omega naught, which is the angle it has. In that case, what you can say is that a magnitude of z naught, for example, is r naught, and the angle of z naught is just omega naught. Okay? So they're both valid representations of these complex numbers. So the first and foremost thing we wanted to consider about z transforms is, why did we even get down this path of talking about z transforms? Was because Fourier transform didn't exist for some sequences. So to make sure that z transform holds up to its promise, we need to find out whether it really does converge. Does it converge or not? And so the question I want to try to answer right now is, does x of z converge? And more specifically, it's not really a binary question, does it converge, yes or no, but more specifically, if you look at this z-plane here, for what values of z does it converge? What you're going to see is that for some values of z, this summation that you have here converges, and for some values of z, it just doesn't converge, okay? So the question, more specifically, I want to know for what values of z does x of z, which is this summation, converge. So let's write down x of z as a definition in terms of its polar coordinates. Summation from n minus infinity to plus infinity, x of n, and instead of z, I'm just going to copy this polar coordinate r e to the j omega, r e to the minus j omega. No, I'm sorry, e to the j omega, the whole thing to the power of minus n. Okay. And then I can rearrange the terms there and write down x of z once again as summation from n minus infinity to plus infinity of x of n. I bring r to the minus n here, and then e to the minus j omega n out. And why did I do that? It's like this. Every time you have a problem to solve, just reduce it to a problem that if you don't know how to solve it, reduce it to the one that you do know how to solve. And why did I do this? Well, because this now looks amazingly like what? The discrete time Fourier transform, the thing it's an object or an animal we've seen before and we know how to deal with. And what do we know about exist? So this is essentially DTFT of this sequence, x of n, r minus n. And what do we know about existence of the DTFT of any sequence? We know that the DTFT of Fourier transform exists, and when I say exist, it's the same thing as the summation converging. We know we already talked about uniform convergence. We know that the uniform convergence happens if the sequence is what? Absolutely summable. So remember that DTFT of x of n, r to the minus n, exists, or in other words converges, those are the same things, if x of n, r minus n is absolutely summable. And what that means is that i.e. if summation x of n, r to the minus n summed over n is less than infinity. That's what I mean by definition of absolutely summable. Okay? So the conclusion that you get is simply this, which is if this condition holds true, if x of n, r to the minus n absolute value is less than infinity, then z transform exists and it converges. That means it converges. And so what does it tell you about convergence of z transform? What does it depend on? Does it depend on r or on omega or on both? Right. So from here, the main conclusion that you want to get is that convergence only depends on r and not omega. So if I were to draw one more time real part of z and imaginary part of z, I can talk about whether or not this the summation converges only has to do with your distance from origin. Okay? So what that means is that for all the points, let's say, that are distance r0 from origin, have the same convergence properties. Either they all converge or they all diverge. It can't be for this point it converges, for this point it diverges. So if all these points are r0 away from the origin, for example, then either they all converge or none of them converges. It's only an r-dependent property, which means the distance from origin dependent property. Okay? And what else does this, the fact that it depends on R, what other thing does it tell us about region of convergence? What shapes would those regions of convergences have? Yeah, there will be either like circles, or there will be rings. There will be things that are always radially symmetric, because they're only R dependent. They're not omega dependent. Okay, so that means region of convergence is always radially symmetric. That means if x of z converges, for example, for z equals r naught e to the j omega naught, then it also converges for z equals r naught e to the j omega 1, or r naught e to the j omega 2, etc. It also converges for all of this. It's not, in other words, not angle dependent. The convergence is not angle dependent. It's only distance from origin, which is R dependent. Okay? So that brings us sort of to a good point to define and talk about what we call region of convergence. Okay? ROC, which stands for region of convergence. And what does that mean? I'm going to let you guys define it. What is the region of, what's the definition of region of convergence? It's a region in the z domain for which this summation converges. The name is on it. For which this summation, x of n, z to the minus n, converges. Okay? That means Z transform exists. And based on the discussion we had up here, okay, if you can roll up the camera to cover half of this page, thank you. Based on the discussion we have, ROC, what are the possibilities that for ROC are what? There can either be, I don't know, inside of some circle. What other possibilities are there? It's only R dependent and not omega dependent. What else can it be? Or it can be outside of some circle. Or it can be what? Between two circles. In that case, it's called a ring. Or what else can it be?
Plane and you subtract the ring.
Yeah, you can have the entire plane but subtract a ring. Or you can have just a point. The origin, for example. A point, i.e. origin.
You have a circle?
That's also possible. But that gets into singular cases. We'll talk about that a little bit. Yeah.
Is it possible to define a Z transform at the origin? Because taking Z power minus n, right?
Yeah, you could say the summation converges only when R is equal to 0. That's what I mean by a point.
So, in that case, Z is 0. So is Z power minus n defined?
For some values of n, yes. I'll give you examples of where the thing is only defined at the origin. Okay, just hang on there. Or it could be at infinity. It could be that it converges everywhere except at infinity, or it could be that it converges just at infinity. All of those are possible. Okay, it just has to be not angle dependent. That's the main thing. Okay, so the next thing I want to talk about, having said all of these things, is that let's come back to a new page. Is that what I claim is that if I just give you an x of z by itself, that doesn't define any sequence, doesn't uniquely specify a sequence. And you always have to have a region of convergence attached to it before you can uniquely talk about the specific time domain sequence. So x of v by itself doesn't uniquely specify a sequence. always need ROC, or region of convergence. So in other words, an x of z plus ROC1 could correspond to some sequence x1 of n, and then x of z plus a different ROC, ROC2 for example, would correspond to x2 of n. Entirely two different sequences. And can anybody think of an example that for which this is true? Can you think of a x of z with two different region of convergences and corresponding to two different time sequences? Good. So what he's suggesting is 1 over 1 minus 2z inverse. Or let's make 2 more general, call it a. Okay? And so what are the possible regions of convergences for this? Well, this one has a pole at a. And once you have a pole like that, what are the possibilities of regions of convergence? Yeah, it could be either outside the circle or it could be inside the circle. And why is it that having a pole here just limits your region of convergence to two regions only, one of two possibilities? Because as we'll talk about later in the same lecture, region of convergences cannot include poles. Why? Because at the pole, which is for example z equals a, you get 1 minus a times a inverse, so 1 minus 1, which is 1, 0, so you get 1 over 0, and the thing blows up. You don't even have to worry about any sequence converging or non-converging or get your hands dirty with that. The thing just blows up. So for sure, x of z cannot possibly converge at a, and because we just talked about the fact that convergences or region of convergence is not angle dependent. If it doesn't converge at A, it doesn't converge at any point on this circle. So the thing, this summation here, if you were to write the summation for the sequencer, it blows up on all the points here. So region of convergence cannot possibly include that. But also region of convergence is a contiguous sort of region. So this circle essentially has divided up our plane into two regions, outside and inside. There are some conferences in which mathematicians argue for days at a time what's inside the circle and what's outside, but we don't get into that discussion here. Okay, now coming back to this discussion we were having here. So what are the so ROC1 could be this, and our ROC2 could be this. And if I pick ROC1, what kind of a sequence will I get as my inversely transform? Yeah, you get a right-handed sequence. And if I pick ROC2, I get a left-handed sequence. Right-handed sequence means that it's non-zero for values of n getting larger and larger. Right-handed sequence. Okay. So let me just sort of reverse that. So what is the inverse Z transform of this sequence anyway? So let's write down the two possibilities of what are the possible inverse Z transforms here. You could have x of n equals a to the n u of n, which means this is a right-handed sequence as a function of n. Okay, which means that x of z is summation from minus infinity plus infinity a to the n, z to the minus n, u of n, which is a summation from n equals 0 to infinity a to the n, z to the minus n, which is summation from n equals 0 to infinity a z inverse to the n, and that's a geometric series. And this thing converges right here. It converges if a z inverse is smaller than 1. That means that z is larger than a. And what does it converge to if all of these things holds true? It converges to 1 over a z inverse. And what does this convergence criterion mean? It means that this is the region of convergence. Okay? So this x of z, together with this region of convergence, which we call ROC1, results in this sequence in time domain, a right-handed sequence in time domain. On the other hand, a different x of n, example 2, if I have x of n equals minus a to the n u of minus n minus 1, and what do I mean by that? Well, that's a left-handed sequence. It's a function of n. It starts at minus 1, and it goes on, like that. This is u of minus n minus 1. And then you multiply by minus 8n, so it does all kinds of funny things, but it's non-zero here. So this is what we call a left-handed sequence. And what we have is x of z is equal to minus summation from n minus infinity to minus 1 of a to the n, z to the minus n. And then you do a change of variable, which is m equals minus n. And you get x of z is equal to 1 minus summation from m equals 0 to infinity, a inverse z, the whole thing to the power of m. So that's a change of variable. And then, under what conditions does this summation converge? This converges if what? A inverse z is smaller than 1, which means that z is smaller than a. So, and if it happens, then the answer you get is 1 minus a z inverse. And what does this condition mean? That means you're looking at inside of a circle. So this is the region of convergence for this sequence. So this sequence with this region of convergence has the same x of z as this sequence with this region of convergence. So a right-handed sequence with region of convergence outside of this circle has the same x of z as this left-handed sequence with ROC inside. Okay? Any questions? Is this mostly of tutorial review type nature for most of you? Yes? Let me ask you this. Who hasn't seen the material I just covered today before? You haven't. And you haven't, and you haven't. And what course are you grad student or undergrad? Or?
Grad.
I see. So you haven't seen Z transforms in your signals and systems. Laplace transform, for example. And you guys? Same, also grad students. Okay. You might want to listen in 120 when there's like a multi-week or multi-lecture representation of the Z transform stuff. I think both, how about the Kahn group and Gaspar, he already told me he spent a lot of time on Z transform. Is that correct? Is the Gaspar group, have you guys seen this stuff? Okay. And the Kahn group. I wish that my class was more region-oriented. Like, I look this way, it's Kahn. Look that way, it's Gaspar. And this way is grad students, but it doesn't work. It's just dispersed. So. Now, the Kahn group. Have you guys seen a region of convergence in Z? Okay, good. Thank you. Okay. You might, for the three of you who haven't seen Z transforms before, you might also want to watch the lectures of 123 from previous years. I used to put more emphasis on it before 120 covered it. And those are all in videotapes. Goes back all the way to 1990 almost, so you can watch me as I age, like in 12 years. No gray hair, no lines, and now, you know, full. But there was more Z transform 10 years ago than it is now. Yeah.
Well, I just have a question about the Z transform.
I was just wondering if the Z transform doesn't include the region of convergence doesn't include the unit circle. Does the system, do we really know anything about it for useful signals? Because it seems like the only signals we apply are on the unit circle.
Not really. First of all, at this point, you use the word systems and signals both in your questions, okay? But that's not a bad thing. There's signals that we process, and then there's systems. Systems that are LTI that have an impulse response. That impulse response has a Z transform. This discussion, I've kept it at a fairly general level, right? I'm only talking about Z transform of signals, and that signal could be a real live signal from its sensor or device, or it could be the impulse response of an LTI system, right? It could be either one. Now, one thing I did not mention, and I'm glad that you brought this up, is that given the relationship between Z transform and Fourier transform, what can we say about the Fourier transform of a signal existing? Well, the Fourier transform of a signal is the Z transform evaluated on the unit circle. So if the Z transform's region of convergence includes the unit circle, then that signal also has a Fourier transform. So let's go back to this picture we had at the beginning. Well, I didn't really draw a picture. Well, here. Yeah, this one. So here, what I was talking is this is unit circle, the one radius. So if I remember, I told you if I cut the Z transform with a knife along this circle, I get this periodic function. So I start from here, which is here, and as I go around, omega changes all the way to come back to 2 pi, then I'm here again, and then it goes on and on. So going round and around the circle corresponds to this thing being periodic, right? So what do I mean by what can we see now that the Z transform is the Fourier transform is Z transform evaluated on the unit circle? What can we say about the existence of Fourier transform? Well, if the region of convergence of Z transform includes unit circle, that means the Fourier transform exists. That means on the unit circle the thing converges. That means that's one of those signals for which Fourier transform would have existed. Now, there's also issues related to stability that we will talk about a little bit later, and causality and things of that nature. Okay. Okay. So here are some fairly general discussions about how important region of convergence is in defining a Z transform. And just I want to wrap up with one more example, and that is, how about if I have a sequence like x of n equals 1/2 to the n u of n plus minus 1/3 to the n u of n. In that case, x of z is given by summation from n equals 0 to infinity of 1/2 z inverse to the n plus n equals 0 to infinity of minus 1/3 z inverse to the n. And this thing has a region of convergence for z larger than 1/2, and this thing has a region of convergence z larger than 1/3. Okay. And what do we get here? Well, this one only converges if this is 1/3 and this is 1/2. We're outside of this circle. And this one only converges outside of that circle. So what does it mean? What's the total region of convergence? Is it the union of these two regions, or is it the intersection of these two regions? It's the intersection of these two regions. Why? Well, because let's say I pick this point, which is in this guy's region of convergence, but it's not in this one. What does that mean? That means this summation blows up, but this summation doesn't blow up. I mean, the other one. This summation blows up, where this one doesn't blow up. Well, what happens if you add up something that's finite to something that blows up? Do you get blown up or finite? Blow up. So that's the reason for intersection. So it's the intersection of these two things, which in this case is outside of this thing. Okay. So the region of convergence for the whole thing is z larger than 1/2. And finally, this is another example of being outside of some circle. And how about an example like this? x of n is equal to minus 1/3 to the n u of n minus 1/2 to the n u of minus n minus 1. What can we say about that? Well, this thing converges for z larger than 1/3. This thing converges for z smaller than 1/2. So this is 1/3. This is 1/2. So that's the intersection of those two things here. Okay. And what can we say about this sequence? Is this a right-handed sequence? Well, come back here. Was this a right-handed sequence or left-handed sequence? This was a right-handed sequence, and no wonder the region of convergence ended up being outside of some circle. Come back here. Is this x of n a right-handed or a left-handed? It's called both-handed because it's got a component that non-zero for n turning to infinity. It has a u of n, and it has a u of minus n minus 1, which non-zero all the way going to minus infinity. So this is what's what we call a both-handed sequence, and therefore there's no surprise that region of convergence is a ring. Okay. And finally, the last example I want to show is, Z transform is not a cure-all type of a transform either, in a sense that there could also be sequences for which the Z transform doesn't exist. So suppose I have x of n is equal to minus 1/2 to the n u of n minus 1/3 to the n u of minus n minus 1. So this one converges for z larger than 1/2, and this one for z smaller than 1/3. And here, what's the intersection between these two things? Can you be larger than 1/2 and smaller than 1/3 at the same time? No. So what that means is that the Z transform here just does not exist. Okay. Question?
What happens to the regions of convergence if we take a Z transform of a sinc function?
Well, I don't know off the top of my head. I have to calculate it. So you have a sine of something over n. Right. Where the region of convergence is, I'm not sure. Certainly, the sinc function doesn't converge, as you know, its summation doesn't converge in a uniform sense. So whether or not it includes unit circle, I don't know. And what its Z transform is, that's even a better question. I have to think about that. And, come see me at the end of the class or the office hours, or maybe next lecture at the beginning of it. I'll think about it and get it back to you. If I were to speculate without doing the actual summations and the multiplications and convergence type thing, my speculation is that it's a both-handed. It can't be outside of a circle. It can be inside of a circle. It's probably some sort of a ring because it's a both-handed sequence. But it could be a ring of width almost 0. It could just have sort of be a special sequence that it just converges on the unit circle, but if you minimally perturb from that, maybe it would not. But I have to think about that and see if there's sort of a formal derivation one could come up with one way or the other. Make a note of that. So you're talking about ROC essentially of a sinc function. Anybody knows the answer off the top of their head? Either they've seen it or thought about it before?
Isn't region of convergence to absolute sumability?
Yeah, that's why I'm not sure.
Absolute sumability for that sequence that
You don't.
technically has a region of convergence.
That could be my guess, but it could be that. That's why I say it could be just a circle. It might just be a circle. I doubt it though.
I don't think that would imply one.
No, but we didn't. We said if the sequence is absolutely summable,
Right.
then the thing exists. But it didn't go. It's a necessary, but it's not might not be sufficient. You see, it doesn't go the other way necessarily. Absolute summability, in fact, is is a bit of a stringent condition.
I think what we usually do is
Mhm.
you kind of relax what you consider. So if you wanted to draw a picture, I think you relax what you call convergence, and you start talking about this, the mean squared error convergence. And
Right.
you might be able to do something.
Right, right. So in a uniform convergence sense, it doesn't. We know because it's not absolute summable. But we talked about the fact that it's a mean square error convergent. So maybe maybe in that sense. Okay. So let me. So having said all these examples, what can we say about let me do one more example. Sorry, and that's an example of a fine. Let me make the observations. Keep flipping back and forth. So the observation is that if I had a right-handed sequence, ROC is sort of outside of some circle. If I had a left-handed sequence, ROC is inside of some circle. And if you have a both-handed sequence, then it could be a ring. Or it could just not exist. This was the example we just had. Or not exist. And the only thing I didn't tell you about is what if the thing is a finite length sequence? What can you say about that now? Well, let's do an example just to clarify. So let's say x of n is equal to a to the n in the range of n minus 1 and 0 otherwise. So then x of z is given by 1 minus a z inverse to the n over 1 minus a z inverse. And how do I get that? The formula for some geometric series, right? Or alternatively, I can write that as 1 plus a z inverse, because x of z is just the summation x of n z to the minus n. This is some of the simplest thing the students always forget about, and that is there's all these infinite geometric series and tricks you can do to find out what x of z is, but the definition itself is also a good source. 1 plus a z inverse plus a squared z to the minus 2 plus dot 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 plus a to the n minus 1 z to the minus n plus 1. So what can we say about the convergence of this thing?
The whole thing except the origin.
That's correct. So it's 1 plus a over z plus a squared over z squared plus da 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 plus a n minus 1 over z n minus 1. So you can easily see that if you have a over z and if z is equal to 0, this term blows up, this term blows up, they all blow up. On the other hand, if z is not equal to 0, as long as z is finite, this thing will never blow up. So that means that the region of convergence of this, of x of z, is everywhere except at origin. Okay? So origin meaning z equals 0. Okay? So what else? So for a finite length sequence of this kind, that's sort of another possibility. So to summarize properties of Z transform. Can't hear you. Could you use the mic so I can at least hear you? Sorry. Mm-hmm.
I mean, so if the other duration is in the left hand side.
If what's in the left hand side?
Other duration, other signal.
Another signal.
I mean that x and n is also always less than 0.
Oh, if you had non-zero values of x of n for negative values of n.
Yes, so the origin can also be convergent, right?
cannot or can be? Okay, are you making a statement or a question? Okay, so what you want me to consider is that if I have x of n, let's say equals to a to the n or something like that, for n negative values, like minus n to 0. Okay? So what you would get then is x of z summation from n equals 0 to minus n of a to the n, z to the minus n, which would be 1 plus a inverse z plus a minus 2 z squared plus da 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 plus a to the power of minus n z plus n. And so for what values of z does not converge for? That's right. So it converges for every value of z except for when z itself blows up. So it converges everywhere except at z equals infinity. Okay? Because when z tends to infinity, these terms blow up. So if it is a finite length, it all depends on... And how about the finite length has both powers of z and powers of negative z? Then what happens? Let's say it goes from minus 5 to plus 5. Well, then it will blow up at z equals 0. It'll also blow up at z infinity. So it converges everywhere except for at 0 and at infinity. So everywhere but subtract 0, subtract infinity. Okay, so it has to do with powers of which indices of n it is that it's non-zero. Did that answer your question? Good. Okay, so moving on, what can I say about properties of Z transform? So number one, ROC is a function of R and not omega. That we already talked about. The other thing we can say is that Fourier transform exists. This is another question that was brought up. If ROC includes unit circle. And finally, the last thing I want to say is that ROC cannot include a pole. And we talked about that already. So if I have 1 over 1 minus half z, then this is a pole at location 2, and ROC cannot include any point in this circle, because at 2 it blows up, and therefore at all other values of z which have magnitude or radius 2, it also blows up. Okay? And the other properties are sort of continuation of what I had up here, which was, if I have, I started writing it down up here, some observations. If you have a right-handed sequence, it's outside of some circle, left-handed sequence inside. Both-handed, it's ring or not exist. And finally, the last observation I want to put down is if I have a finite length, which is what we just did right now, we have a finite length sequence, what happens to ROC? It's everywhere except at z equals 0 or z equals infinity, or both. Okay. So rather than doing this, leaving this by example alone, which is if you have a right-handed sequence, ROC is outside of some circle, I like to spend the next 2 minutes or so proving one of these properties. And why is it that if the sequence is right-handed, ROC is always outside of some circle? So let's do that. So I want to show that if the sequence is right-handed, then ROC outside of some circle. Okay. So what do I mean by that? So what is the exact definition of right-handed sequence? that means if it is non-zero for n naught, then it's also non-zero for n larger than n naught. So that's the definition of having a right-handed sequence. If I have a sequence x of n that's right-handed, then this is true. Okay. And what do I mean that by R of z is outside of some circle? What that means is that if x of z converges for r at r naught, then it also converges for all r that are larger than r naught. That's what we mean by technically translating the word ROC outside of some circle translates into this condition, which is if x of z converges for r naught, it also converges for all the r's that are larger than r naught. Okay? So what I'm going to do is the proof. I'm going to assume for now that it converges for some r naught. Okay? We're going to assume that x of n, we assume that x of z converges for some r naught. And to prove my thing, I have to show that it also converges for r larger than r naught. And then show that it also converges for r larger than r naught. That's my goal. Okay? So what does it mean when I say my assumption that it converges for some r naught? What does it mean technically in equations, in mathematics? What does that mean? What was the condition for convergence? Something had to be absolutely summable. What was the thing that had to be absolutely summable? Yeah, but what's the expression? I have this sequence x of n, and I know it's x of z converges for r naught. Mathematically, what is true then? Speed up. Yeah, go back to the beginning of the lecture where we talked about that means this is absolutely summable. If x of z converges for r naught, that means the sequence x of n r naught minus n is absolutely summable. That means x of n r naught minus n absolute value is less than infinity. This is page 2 of today's lecture. So that means, so this assumption just implies that summation from minus infinity to plus infinity of x of n r naught to the minus n is less than infinity. So this is, based on this assumption, this is true. And if that's I'll get to that in just a second. So now I'm going to invoke my right-hand sided condition. Sorry, when I have a sequence right-handed, I want to change the definition of my n naught. I wrote sort of the wrong thing here. That I'm going to assume that this, if the thing is right-handed, that means if it's non-zero for n naught and larger values of n naught. What I'm trying to say is that it starts at somewhere n naught and it's non-zero from then on. That's what the right-handed sequence means. So because it's right-handed sequence, I don't have to worry about the summation changing from minus infinity to plus infinity. I can just say this is summation from n equals n naught to infinity, because the right-handed assumption, right-handed side assumption just kicks in going from here to here, and that x of n r naught minus n is less than infinity as well. So this is true and this is true. I can easily say that. Now I want to show that it also converges for r larger than r naught. Okay? So what does it mean? So this is true. Based on my assumption, this is true and this is true. And what I want to show, can you zoom up, cover half of that page? Yeah, I want to show that, what do I mean mathematically that it also converges for r larger than r naught? It means that for r larger than r naught, I want to show that this thing x of n r to the minus n is also absolutely summable. n equals n naught to infinity. This is not true. This is, I want to show this. Still to be shown. Okay. Well, how can I show, knowing that this is true and I want to show that, how can I show that? Well, we can write down the thing here, x of n r to the minus n, as the follows. You can say it's x of n times r naught to the minus n times r over r naught to the minus n, absolute value. I'm just multiplying the numerator and the denominator by r naught minus n. Okay? Now I can separate these two terms. I can say this is x of n r naught minus n times r over r naught to the power of minus n, absolute value. And so I want to show, so the thing I was going to show was this thing, so that means the thing I want to show is that for r larger than r naught, this n from n0 to infinity of, and now I'm going to replace this thing with this new thing I have, x of n r naught minus n times r over r naught minus n is less than infinity. This is again what I want to show. Okay? And I know that this is true. We know that this summation doesn't blow up, and I want to make sure that for r larger than r naught, this summation doesn't blow up. Well, that's easy to show. What can we say about this term? Because r is larger than r naught, this number here is what? R over r naught is larger than 1. So I have some number. Let's plot this sequence. If I were to plot it as a function of n, from n naught onwards, I have a number that's larger than 1, that's to the power of minus n. So let's say n naught was, I don't know, 10 or something like that. And r over r naught is a number larger than 1, let's say it's 2 or something. So it's 2 to the power of minus 10, to the power of minus 11, to the minus 12, etc. So it's a dying sequence. So because r is larger than r naught, that means r over r naught is magnitude smaller than 1. And because this is a right-handed sequence, now the right-handed assumption kicks in one more time, right-handed sequence, and we only consider powers of n increasing, that means that's a dying sequence. That's a decreasing sequence. And therefore, because this summation here already was absolutely summable, x of n r naught minus n, you can easily conclude that this whole thing is absolutely summable. So this fact that this ratio is smaller than 1, and the fact that the summation goes from n naught to infinity, and this is powers of negative n, that makes this thing not affect the convergence of the whole thing. Okay? So this was so I wanted to show the proof mathematically so that you can have at least one experience of seeing how some of these things are proven. The trick is you want to use all your assumptions. If by the time you're done you didn't use any of your assumptions, that means there's something wrong with your proof. And the other trick is you want to translate these words into precise mathematical statement. What does it mean it's outside of some circle? What does it mean for it to be right-handed, etc.? So is this more or less clear?
You assume n0 is n naught is larger than 0, so it's easy to see a dying sequence.
But even if n naught was not, it still would have been a dying sequence. The fact it's the right-handedness that makes it a dying sequence, not whether n naught was positive or negative.
I mean, if n0 is less than n0 positive n0, so it will first go up.
Yeah, it'll look like this. But it's still, as time goes on, as n goes on, it dies like that anyway. What he's talking about, if n naught wasn't positive but n naught was negative, it would be doing that. But still, the fact is that because it's right-handed, this is a exponentially decreasing sequence. Yeah. Mm-hmm.
Do we have to have every n larger than n0 non-zero, or could we have some zero terms?
You could have some zero terms, but then it should sort of continue and have more non-zero terms.
Okay.
Yeah. Yeah. I'm assuming, because I had to show it for r larger than r naught. Why did I have to show it for r larger than r naught? Because I'm proving outside of some circle. What does outside of some circle means? Means r larger than r naught. So essentially, I started off by assuming r naught was in the region of convergence, and I said, now I pick an arbitrary r larger than r naught because I want to show outside. So that translated into r larger than r naught. Okay. Okay. Let me just see if we can wrap up the lecture, or just so another way of seeing, since I came all the way down here, let me make one more comment down here. Another way of seeing that this thing is less than infinity, you can write down this summation here, okay, as a let's not talk about that. I think that confuses the issue more than necessary. Let me talk a little bit for the next 5 minutes about inverse Z transform. Again, I want to sail through Z transform fairly quickly. So if I have an x of n that has an x of z, and we talked about convergence and all that, now we have to talk about how can we recover x of n from x of z. And I'm just going to write down the expression for x of n, which is 1 over 2 pi j, a contour integral in a counterclockwise direction of x of z, z to the n minus 1 dz. Now, how many people have seen this integral before? Okay, so some. So what does this mean? So this is a, what do I mean by this thing? That means any closed contour, and I'll explain it in just a second, in ROC of x of z, z to the n minus 1. So what do I mean by all of these things? Well, x of z is a function of a complex variable z. It has a real part and an imaginary part. It's a two-dimensional function sticking out of this page, okay? And there's a thing in complex variable theory. It's called contour integration. What that means is I have an arbitrary contour here, okay? And I can start from here and take on the value of x of z and then integrate it, add it to this along this contour, okay? So if I have a contour, I can integrate a complex function of a complex variable along it like that. And then I get a number. And what this is telling you is that if I pick my contour, any closed contour, closed means you start here, you end up there. If I pick any closed contour in the region of convergence of this, and I do this business of contour integration, I get my x of n back. Okay? And how do I do contour integration? Can anybody tell me? There's one theorem in applied math that allows you to do contour integration. And what's that? Huh? You can do residuals. What do you mean?
Integrate around the pole.
Uh-huh.
I'm not really sure.
Was this discussed in either Kahn's or Gaspar's? Okay. So the way you do this thing is called Cauchy's residue theorem. So let me talk about that. And we won't prove it, but we'll tell you what it says. And Cauchy's residue theorem goes like this. It says if I want to do contour integration 1 over 2 pi j of over any C closed contour, if I have a contour C that's a closed contour. By the way, this arrow means that I'm integrating in a counterclockwise way. I have a closed contour, and so I'm going this way rather than clockwise. It turns out if you integrate clockwise, you get the negative of the answer you would have gotten if you integrate counterclockwise. The same way as if I have a function f of x as a function of x, if I integrate it from a to b, I get the negative of if I integrate it from b to a, right? The same thing holds true here. So counterclockwise is sometimes, as the years go by, you guys are so used to digital watches, I have to explain to you what that means. But if you don't, just there's a clock there, and you can see Counterclockwise. I had one question one year saying, what does that mean? They must not have taken physics or anything. But anyway, so this is what Cauchy's residues theorem says. It says counterclockwise integration of f of z dz is the summation of all the poles of the residues of f of z at each pole of f of z inside contour C. Okay? So here's f of z guy. This is the z domain. And f of z has got a pole here and a pole here, call it P1, P2. And the contour that I picked to do my contour integration could be this, in which case I have to compute the residue to do this pole and the residue to do that pole. Or it could be this, in which case I could only compute the residue to this guy. Or it could be just this, in which case there's no poles inside my contour, and therefore there's no residue contribution, in which case I just get 0. So what answer I get has to do with how many poles my contour encircles or encloses. And now I still didn't tell you one other thing. What do I mean by residue of a pole? What's the definition of that? And I'm going to do that right now. If f of z is written as a function phi of z over z minus z naught to the power of s, then the residue of f of z evaluated at z equals z naught at the pole. So this is a pole of order s. S could be 1, it could be 2. If it is 1, then you have a simple pole. If you have 2, you have a double pole, etc. So the residue evaluated at z equals z naught is defined as 1 over s minus 1 factorial, the derivative of the s minus first derivative of phi of z with respect to z, evaluated at z equals z naught. So that's the definition of residue. If I have a pole at z naught, which is an s order pole, that's such a hard thing to say, then this is the residue. Okay, so what do I mean? Let's just give you a quick example of a residue. What do I mean by that is that if I have f of z is equal to 1 over z minus 2 squared, so what is the residue of f of z at the pole, which is z equals 2? Well, staring at this thing, then phi of z is equal to 1, s is equal to 2, and z naught is equal to 2. So the residue of f of z at z equals 2 is equal to 1 over s is 2, 2 minus 1, 1, 1 factorial 1, and then s is 2, so I take the first derivative, so d dz of phi of z, and phi of z is just 1, well, that's 0. So that's it. The residue of f of z at z equals 2 is just 0. Not too bad. Now, what if f of z was something slightly more complicated? Example again, let's say f of z was z cubed over z minus 2. Then in this case, phi of z, once again, I want you to see this. Could you go up a little? Thank you. And that's it. In this case, phi of z is z cubed, and then the z naught is just 2. And s, the order of the pole is just 1. So it's so residue of f of z at z equals z naught is equal to 1 over 1 minus 1 is 0, 0 factorial is 1, so 1. And then s is equal to 0, so that means that s is equal to 1, so I'm not taking any derivative. So it's just phi of z evaluated at z equals z naught, and phi of z is just z cubed evaluated at z equals 2, so I just get 8. That's what the residue of f of z at 2 is for this f of z. Okay? So what does it mean? What does Cauchy's residue theorem tells me then? Well, it tells me that if I was going to integrate, this is the z-plane, and this is my last comment here. If I was going to integrate this function for these various f of z's, So I had f of z a pole at z equals 2. Let's do that. So if I was going to do 1 over 2 pi j of, could you please stop murmuring here? It's very disturbing to the lecture. Thank you. So if I do a contour integration of f of z dz, just like we have here, what answers do I get? Well, if my contour is over here, contour C1, for example, I have no poles inside of it, so I get 0. With this f of z I'm talking about here. And if my contour is funny looking thing here, but it does circle, it encloses this pole z equals 2, then I have to count the residue for that thing. So over C1 it's equal to 0, but over this contour C2, 1 over 2 pi j of over contour C2 of f of z dz, what's the answer? It's the residue due to this pole, which we just computed to be 8. So that's it. So what answer you get in your contour integration has a lot to do with how many poles you encircled in your closed contour. Now you can put 2 and 2 together. This is Cauchy's residue theorem, together with the expression for the z transform. Stare at these two things. This is how you do inverse z transform, and this is Cauchy's residue theorem. Just really handy, telling you, you just figure out the poles of this thing, compute the residues due to those poles, and add them up. So if there's one pole, or if one pole is encircled, then that's just the residue to that one pole. If 5 poles are encircled, it's the residue to that 5 poles. The most impressive thing about Cauchy's residue theorem is that, yeah, it escaped my mind. The most impressive thing is that it doesn't matter. It only matters how many poles are encircled. It doesn't matter what the shape of the contour is. The contour could be circled, it could be a wiggly line, it could be a dancing wiggling line, whatever it is. All that matters is how many poles it encircles. As long as the poles that it encircles is the same, the answer you get is always the same. And to me, when I was a student, that was extremely amazing. And it relates to some of the stuff you learn in Green's functions and Green's theorem in physics in electromagnetism, which is the contour integrals of some other stuff is always the same, no matter what path you take. So I'll talk next time about using this Cauchy's residue theorem to actually compute inverse z transform. Pick up the solution on your way out. It's right here. Yeah.